In the previous video, we talked about one fundamental HMM task, which was determining the probability that a sequence of observations fits a given HMM. In this video, I'll cover a different fundamental HMM task, decoding, and I'll focus specifically on the Viterbi algorithm as a way of doing so. I'll cover the intuition behind the Viterbi algorithm, walk through the algorithm itself, and then go over a case example to show what it looks like in action. And decoding is the process of answering the question given an observation sequence in an HMM of what is the underlying state sequence that generated it. Usually there are multiple possible state sequences, but we want to select the one that is most optimal or that best explains our sequence of observations. Decoding is very useful for sequence labeling tasks, such as part-of-speech tagging. And just like with finding the observation likelihood, there is an easy, naive solution to decoding. For each possible hidden state sequence, you could compute the probability of generating your sequence of observations given that state sequence, and then you could select the state sequence with the highest probability. Again, there's nothing fundamentally wrong with this strategy, it's just super computationally inefficient. So to decode sequences more efficiently, we can use the Viterbi algorithm. The Viterbi algorithm is yet another dynamic programming algorithm, just like minimum edit distance and forward algorithm. In some ways, you'll see that it's actually quite similar to both of those. When computing the Viterbi algorithm, our goal is to jointly compute the probability of the observation sequence and the best state sequence. So to do this, we just recursively compute the probability of the most likely subsequence of states from time step 1 to t, ending in the current state at time t. Since we want to return the most probable state sequence, we also record back pointers along the way, just like we did when computing the minimum edit distance. This allows us to easily backtrace through the most probable state sequence once we're finished. Here's the more formal pseudocode for the Viterbi algorithm. We see that we start by just creating a probability matrix of size n plus 2 by t. Next, we'll initialize everything for the first time step. So we'll loop through all of our states, and for each state, we'll initialize the Viterbi probability to the product of the transition probability from the start state to the current state q, times the observation likelihood that the first observation in our sequence was generated by state q. We'll initialize the back pointer to 0. And then we can move onward to the rest of our sequence. For each time step from time 2 all the way to t, we'll loop through each state q. Within that loop, we'll set the Viterbi probability for the given state and time step to the product of the Viterbi probability for state q prime at the previous time step, times the transition probability from q prime to q, times the observation likelihood that the observation at the current time step was generated by state q, where q prime is the state from among all possible states, 1 through n, that maximizes this equation. We'll set the back pointer for the given state and time step to q prime itself. Finally, once we're finished with that loop, we'll set our final Viterbi probability, or best path probability, to the maximum of the Viterbi probabilities we computed for all states q from 1 to n at time step t. We'll set our final back pointer, or best path pointer, to the state that maximizes the previous equation. Then, to find the best path, we just start from there and trace our back pointer backward until the first time step. So you might have just been considering that algorithm and thinking, wow, that looks really similar to something or some things that I've already seen. And you're correct. The Viterbi algorithm is basically just the forward algorithm plus back pointers, and substituting a max function in place of the summation operator, both of which we saw with the minimum edit distance. So you basically already know everything. I'll work through an example anyway, just to highlight the differences more clearly. We'll work under the premise of the same ice cream problem that I talked about in the forward algorithm video. So if you're watching these out of order and haven't seen that one yet, you may want to pause this one and go back to review the forward algorithm. Or if you prefer this way, you can just pick it up on the way as we go. So to quickly review, here we have what was previously called the forward trellis, but now we're calling it the Viterbi trellis. We have a set of states at time steps 1, 2, and 3, a start state, and an endpoint. We also have a sequence of observations, 3, 1, 3. Our goal is to figure out which sequence of hidden states generated the observed sequence 3, 1, 3. So we'll start out by computing the probability that the first state is hot times the observation likelihood of eating 3 ice cream cones given that it's hot, and the probability that the first state is cold times the observation likelihood of eating 3 ice cream cones given that it's cold. This is identical to what you already saw with the forward algorithm. So here are our first Viterbi probabilities. Moving on, we'll compute the probability of the second state being hot, given that the first state was hot, times the likelihood of eating 1 ice cream cone given that it's hot. And we'll compute the probability of the second state being cold, given that the first state was hot, times the likelihood of eating 1 ice cream cone given that it's cold. We'll also compute the probability of the second state being hot, given that the first state was cold, times that probability of eating 1 ice cream cone given that it's hot. And we'll compute the probability of the second state being cold, given that the first state was cold, times the probability of eating 1 ice cream cone given that it's cold. Now here's where we deviate from the forward algorithm a bit. To compute the Viterbi probability in the second time step and all subsequent time steps, we take the maximum of the incoming values, where the incoming value for a given option is its most recent Viterbi probability times the product of the transition probability and observation likelihood that we just computed. So for example, to compute the Viterbi probability for hot at time step 2, we would take the max of 0.32, that's the Viterbi probability for hot at time step 1, times 0.14, which is one of the values we just computed, and then 0.02, that's the Viterbi probability for cold at time step 1, times 0.08, which is another of the values we just computed. So the maximum of those two options is equal to 0.0448. The maximum of the bottom two options is 0.048. We continue onward, so now we compute the probabilities dealing with the transition from hot to cold, cold to hot, or cold to cold, while observing that 3 ice cream cones are eaten. And we compute our final set of Viterbi probabilities. So for hot, we need to find the max of 0.0448, that was the Viterbi probability for hot at time step 2, times 0.28, which we just computed, and then 0.048, that was the Viterbi probability for cold at time step 2, times 0.16, which we also just computed. So that's equal to 0.01254. For cold, we'll get the max of 0.0448 times 0.03 and 0.048 times 0.06. So that's equal to 0.00288. So now we can terminate. So the best path probability is just going to be the maximum of our two Viterbi probabilities at the final time step, so 0.01254. If we want to backtrace, we just follow our pointers backward from there. So we know we got our best path probability based on the final state being hot. We know that we got that max probability for the final state based on the second state also being hot. And going even further back, we know that we got that max probability for the second state based on the first state also being hot. So then from there was only one way to transition from the start state to being hot, so we have our Viterbi backtrace. This means that according to the current AQMM, the underlying state sequence most likely to lead to the observed sequence 313 is hot, hot, hot. So now we've covered the Viterbi algorithm. As you saw, the Viterbi algorithm is a nice, simple dynamic programming approach to decode the underlying state sequence for a series of observations, and it complements the forward algorithm well.